Hello, welcome back. Today we're going to talk about polarity, and ultimately we're going to wrap up with this properties of organic molecules document here, which you can work through to understand a lot of the results of the kinds of theoretical things that we're going to talk about first. So I've got a couple pages in the class notebook here. We can start with this blank one and just give you some general definitions, what we're talking about with polarity before we get into kind of more of the consequences or conclusions of that. All right, so first, just a couple definitions here. Hold on a second. Okay. When we talked earlier about covalent bonds, you know, we said that something like this involves two shared electrons. Okay, and that's true. And now what we're going to talk about is what happens when those electrons aren't shared equally. So if you can imagine now these two hydrogen atoms, their two electrons are going in that bond are going to be roughly distributed evenly around each atom. And why would they be distributed evenly? Because there's no reason for them to be more on one side than the other, except kind of momentarily. When I draw this dotted line, by the way, it doesn't mean the electrons are orbiting around like that. I'm kind of trying to draw like a cloud. So imagine a cloud of space around these hydrogen atoms where those two electrons could be. And they could be anywhere within there, but they're no more likely to be on one side or the other. They're just going to be wherever in there. Equal chance all around. Now some compounds, like if we change this to HF, have a different distribution. So in HF, we might draw the cloud more like this to show that the electrons are more likely to be around the fluorine. So one way we can describe that, it's not really a pull, but we can say that the fluorine pulls the electrons toward it. And we have a name for this phenomenon. We call it electronegativity. So atoms that are highly electronegative pull the electrons in a shared bond more toward themselves. Now remember that electrons are negatively charged. So if we have an atom, or if we have a situation like we do in HF here, where the electrons are more likely to be on one side than the other, that means that there's going to be more negative charge over here, because that's where the electrons are getting pulled to. And if the electrons are being pulled toward the fluorine, that means that they're kind of leaving holes. They're leaving non-electron area over here. So this spot is going to be more positive. So overall now, we can say that we have a general positive side of the molecule and a generally negative side of the molecule. And this is what we call polar. All right, so we have a polar molecule, we have a polar bond, and we have that because the electrons are pulled in such a way that they end up being more on one side than the other. Conversely, our example up here, the two hydrogens, we would call this nonpolar, because there is no pull one way or the other, so it's totally even. All right, so the consequence of this is a couple things. First, these types of atoms, or these types of molecules that have these types of bonds, can interact with each other in an attractive way, because we know positive and negative attract each other. So I'm going to just kind of draw a representation of a polar molecule here. So let's say this molecule is like that, where it has a plus and a minus. Well, that means that another one could maybe line up right behind it with its plus and minus, and there would be some attractive force there. Right? So not like a chemical bond, but it's just kind of pulling each other together. And you could even imagine, you know, other ways that these could line up, like opposite each other, right, like that. And so having this type of polarity allows these molecules to line up with each other. This also becomes important when we think about one of the most important molecules, which is water. Now, if you look up values for these electronegativities, you'll find that oxygen is more electronegative than hydrogen. And so that means that in the water molecule, the electrons are going to be pulled toward the oxygen, which means the oxygen part of water is going to be a little bit more negative, and the hydrogen parts are going to be a little bit more positive. And that allows for some interesting interactions. So you can imagine this type of situation with the pluses and minuses going on in water as well. And then that can affect some other things also. So that can affect how likely it is for other molecules to disrupt that water matrix and kind of get in the way. All right. So that's kind of some basic terms. I don't want to get too into all the different types of interactions here because that's what this next document is for. So let's take a look at that. All right, so just like what we've done before, you've seen this, you should be a pro at this by now. These types of activities allow you to discover rules around these compounds, which allows you to remember them much better than if I just kind of told you facts or if you looked them up. So what I want you to do is take a look at this document, and what you'll see is the first page is just a table of a whole bunch of data, some of which might make sense to you, some of which might not. Read it carefully. So it says here, bond polarities are determined by the electronegativity difference between the bonded atoms. That's kind of what we just talked about. Recall that CH bonds are nonpolar. So in our case, you won't be recalling this because we didn't really talk about this, but CH bonds are nonpolar. But CN and CO bonds are polar. Since water is a polar solvent, the more polar an organic molecule, the more soluble it will be in water. And then we've got these tables. So the first one, it says Table 1, polarity, solubility, and boiling points of selected compounds. And then we've got a list of these compounds. They're a little hard to read on my screen. I think it's because of how it came into OneNote, but the original document that's linked in Teams should be okay. All right, so we've got propane, butane, pentane, hexane, heptane. We've got chemical structures. We've got molar mass. We'll talk about that in a second. We've got dipole moment, boiling point, and water solubility. So first, the names. Those are some names of these compounds. We haven't really talked about those yet. That's fine, though. We can just use their names. We've got a table. We've got some structures. This we know about now. So as practice, and actually to help you work through this document, draw each of these as a line structure. So I'll get you started here. This first one, the line structure would look like this, right? 3 carbons. The next one would be like this, like that, and so on. Then we've got some with OHs. So the first one would be 2 carbons and then OH. These down here have an oxygen right in the middle. So you've got a carbon, then an oxygen, then another carbon. And so kind of, I'm giving you an example here, but see if you can draw all the rest of them as well. The next column here is molar mass, which we haven't really talked about yet. Molar mass is related to the size of the molecule. So how big is it? How much does it weigh? Which is then related to how many protons, neutrons are in there. But for this particular document, you can just think of it as a general size. So one thing that it's going to ask you to do later on is to compare similarly sized molecules. So in order to do that, you need to look for similarly sized molecules. So that means you want to compare like this one up here that's 44 with this one down here that's 46, not this one up here that's 44 with this one down here that's 116 or something. So that's just a measure of the size. Then down here you get some more information. Dipole moment is a measure of the polarity of a molecule. So this next column is actually a number that tells you how polar this molecule is. So how much of that separation do we have? Then you've got boiling point, which is the temperature at which the substance boils. And then finally, water solubility. So how many grams of these things can be dissolved in 100 milliliters of water? So as you can see, these are quite low, so only 0.007 grams of propane will dissolve in 100 milliliters of water. And then they go up until you get some of these that are actually in an infinity sign, which means that these are fully miscible in water, which means it doesn't matter how much there is because it's a liquid and it'll always mix with water. So you can have 100% ethanol for this first example here, and you can just start putting drops of water in to lower the concentration all the way until you have way more water than ethanol, and that's always going to mix together. So it's always going to be perfectly mixed together. Anytime there's a number, that means that only that amount in grams can dissolve in water. So the more something dissolves in, or the higher this number is, the greater the solubility in water. The lower the number, the lower the solubility in water. All right, let's start through this. So for this video, if you're watching live, great, hello. But I'm going to ask you to stop at certain points because there are a few points throughout this document that are a little confusing or tricky, and so I want to address some of those. But if you haven't actually completed that yet, don't just watch the video because it won't make any sense. So go through, stop or pause the video when I get to those points, and I'll tell you when to do that. Work through the rest of it up to a certain point, and then come back, and I'll give you some information about that. But let's start it together here. Okay, considering the dipole moments of the molecules in Table 1, which functional group is most nonpolar? So the functional groups are these different groupings. So you have alkane, alcohol, ether, amine. All right, so which functional group is most nonpolar? So what are we going to look at for that? We're going to look first off at the polarity, which is, we just saw earlier, is measured by that dipole moment. So we're looking at this category right here. And of course, the numbers are all different, but we can maybe make some generalizations. Which functional group is the most nonpolar is going to be the one with the lowest numbers in that column. And so very quickly scanning through this, you can see that the lowest numbers in that column are definitely the first ones, because they're all 0. So that means all of these compounds are actually perfectly nonpolar, and therefore those would have the lowest polarity, so we would call these alkanes. Or we would say that these are the alkanes. All right, next question. In general, do polar compounds have higher or lower boiling points than nonpolar compounds? So we're going back to the table, and we say, okay, well, this one's totally polar or totally nonpolar because it's all 0. And then these other ones seem to be somewhat polar because they're not 0. We don't know really how high is high, but we know they're definitely higher than 0. So let's call these our nonpolars and call these other ones polar ones. So in general, do these have higher or lower boiling points than the first group? Now again, it depends a little bit on how you compare. So if you just kind of lump all of these in together, it may not be super conclusive. For example, remember we want to compare similarly sized compounds. Pentane's at 72 and the boiling point is 36. Butanol is 74, boiling point is 118, so that's definitely higher. Diethyl ether is 74, boiling point is 35. That's higher than, oh no, it's not higher. That's actually lower than 36. And then this one at 73 is 77, so that one's higher. So it kind of could go either way. But if we start looking at all of the other ones, you should see a little bit of a trend there. So in general, we would say that polar compounds have higher or lower boiling points, although there are some exceptions that we're going to have to deal with later. So, if we look at the lightest ones, 44 minus 42, 46, 78, 46 minus 23, even 59, 48, that one's quite a bit bigger, so I don't know that we can really say that. But those, definitely the polar ones, were higher than the nonpolar one. All right, so now we go on to number 3, a different question. For each functional group, how does the boiling point change as the molar mass increases? So as we get bigger, do we see a change in boiling point? And we do. So for each category, you should see a trend there as the molecules get bigger. So you can write about that. So then 4, again, they give you some more information. So you should be able to work through most of these until you get to number 8. So if you haven't gotten to number 8 yet, maybe pause this and then go work on that and come back when you're up to there. So for number 8 and number 9, it's asking you to take an inventory of the types of bonds in the compound. Now, in order to do that, you have to draw the Lewis structures, or at least draw a few of them. I would say at least one for each category. So that you can actually see what types of bonds are in there. So are there CH bonds, are there CO bonds, are there OH bonds, are there NH bonds? You'll be able to circle multiples of these for some of them and maybe not for other ones. And there are some other types of bonds that aren't shown here, like CC or CN bonds. But just of the ones that are shown, you're just supposed to circle that. And then that leads you to number 9, which is an important conclusion. What types of bonds tend to lead to these strongest attractions? So once you've looked at the structures of the molecules, and you looked at the types of bonds in those molecules, you should be able to figure out which types of bonds lead to the strongest forces from the stuff you've done earlier. Okay. This is going to be, I'll just put an extra little star there, that's going to be a key point for how you end up understanding this whole thing, and midterm evaluations coming up. This is definitely going to be a big part of it. So take a look at those. All right, so then it gives you some more information. Make sure you read that because it'll help you then going on with the next part. Okay, this is a little bit of a complicated question. So now we're going to start talking more about water solubility. So how much does something dissolve in water? Suppose that we consider anything over about 1 gram per 100 milliliters water to be soluble. Then, considering the water solubilities of the stuff in Table 1, the presence of one polar functional group is sufficient to dissolve a molecule containing about how many nonpolar carbons? Circle one. So what's going on here, it's kind of a confusing question, is if we take one of these categories, like for example the alcohols, what we have here, each of these molecules has one polar functional group. So it has one OH or O or NH, whatever it is. It has one of them. And so it's saying how many carbons can you add before something stops being soluble in water? And this is where we revise what we said a little bit earlier. It's not just polarity that matters. It's not just a molecule being polar, because as you add more and more nonpolar stuff to the end of the molecule, then it kind of stops being polar in the ways that, I mean, it doesn't stop being polar like from the measurement, but it stops like interacting with water in the ways that we would expect polar molecules to do. So for this example, if we look at the alcohols, you can see, okay, if you've got 2 carbons, you're infinitely soluble in water. If you've got 3 carbons, you're still infinitely soluble in water. 4 carbons, now it's not infinite anymore, but it's still fairly high, up at 6.3. And then you add 5 carbons, you go down, and then all of a sudden right here you've crossed that threshold of 1. So the question that we just looked at said, when you drop below 1, we say that means no longer soluble. So here we're saying that these alcohols are soluble in water, and these alcohols are insoluble in water. And you can find a similar line in the other categories as well, where it drops below that. And so it's saying how many carbons do you put on there before you're not soluble in water anymore? And so you can find that. And what ends up happening is that, like, if we take these insoluble ones that have now too many carbons, if we wanted those to be soluble, or if we wanted similar compounds to be soluble, we would have to add more polar functional groups. So maybe instead of 1 OH group, we have 2 or 3. Then we can get more solubility there. All right, we did that. Where were we? here's where we are. Okay. Then it introduces a new category of functional groups called ketones. Ketones are these molecules that have a C double bond to oxygen with carbons on either side. And this time they're only giving you the water solubility data, so not the boiling points, just the water solubility, and asking some questions about that. And then number 2, this is an important one that people often get wrong, but it actually describes it earlier. Go back and read the part that I said to read, the information up here. And if you follow that, it should be clear which of these is correct, and then how you decide, and then you can decide what's wrong with the other one. So that was the information. All right, so now moving down toward the end of the document here, number 5 and number 6 is sort of the goal of this whole thing. This is what I want you to be able to do. When we sit down in our midterm evaluations in a couple weeks, one thing that I'm going to ask you is to rank boiling points and water solubilities of some molecules using only their structures. And so this whole activity plus the supplementary readings that I put up are meant to help you to do that. So can you rank molecules based on their structures? So you've got, for example, A here. So we're going to do one together. If you haven't done this document yet, don't listen to this, because I want you to try this on your own first. Try these out, go through the document, read the stuff, try these out, then come back, and then I'll take you through an example here. All right, let's look at B for our example. So we have 3 similarly sized molecules, and the way this is laid out is maybe confusing about which one is which. So we're talking about these 3. These are horizontally described things. So we're looking at the first molecule versus the second molecule versus the third molecule, and we want to know which one would have the highest boiling point and why. All right, so there's 2 major factors that you'll find that influence boiling point, influence these intermolecular forces completely. The first one that we kind of alluded to is functional group, and that's the most important. So for similarly sized molecules, even not that similarly sized molecules really, the functional group has a huge effect on the boiling point. And if you go back up to those tables, you'll see the alcohols have hugely higher boiling points than anything else. The amines are next. But those types of bonds and that like star that I drew on that important question, whether or not molecules can do that hydrogen bonding that's described in the a little bit earlier in the document, that is the biggest influence on high boiling points. So that's number 1. Then, if you have similar boiling points, we can look at the size of the molecule. And be careful not to mix up this order, because the size part is a lot easier, right? Bigger thing, higher boiling point. That makes a lot more sense. But it's not as important as of an effect. So you have to look at the functional group first, and then you can compare the sizes. Okay, so for this example, these 3 are all similarly sized. They all have about 3 to 4, largish atoms like CNO, something like that. So they're all about the same size. So if we want to find the highest boiling point, we have to look at the functional groups and the types of bonds in the molecule. And the key here is to remember that from all the previous work that you've done, again, stop this if you haven't done that yet, because you want to try it first before you just hear what I have to say. But the answer here is that the second one is the highest boiling point, and it's because of the OH. So having that OH bond in there, that ability to do those hydrogen bonds, makes that the highest boiling point. There's some common mistakes here are, first, to look at the double bond over in this one and say that that one's going to be stronger because of a double bond. That's wrong. It's true that a double bond is a stronger bond than a single bond, but when we boil a compound, we don't break any of the covalent bonds. We just separate the molecules from each other. So the molecules are still intact, they're just separated from each other, but the bonds inside aren't broken. So whether or not something has a double bond doesn't really influence it that much. Another common mistake for this one is, again, with that size thing. This first molecule is bigger than the other two, but not by much. And so unless something is much, much bigger, you're not going to see that size effect. One place where you do see the size effect is in the third one, part C, or number C, letter C, whatever, because these all have the same type of functional group. They all have one OH, and so if you only have one OH, then you have all the same functional group, and you can look at the sizes instead. All right, so you don't have to do this. That's just because of where this thing came from. Let me jump back to the other thing so I can put in some goals here. So the goals, as you can see them on the module reflection, but what you should be able to do is rank molecules. I can't spell molecules today. Rank molecules by boiling point based on structure. Meaning you look at structures and you say, well, this one should have a higher boiling point than this one because of these structural features. And then another kind of part of that, which I also can't spell today, is intermolecular forces, which are what control boiling point. So the higher the intermolecular forces, the stronger the attractions, and the higher the boiling point, the more energy it takes to boil, to split those molecules away from each other. So those are basically the same thing. What's not quite the same thing is our second goal, which is judge water solubility. The reason that's not the same is because molecules with a high boiling point, it could be because they're very big. Water solubility specifically has to do with hydrogen bonding and the ability of those molecules to interact with water molecules. So basically the ability of them to be similar, have similar structures to water. And if you have enough nonpolar parts on your molecule, carbon and hydrogen and such, it's not going to be soluble in water. If you go back to the previous video about the biodiesel structures from last week, you can see that a triglyceride, a fat, has polar functional groups. It has CO bonds, and even the fatty acids have this OH here, which we know is good for dissolving in water. But these are insoluble in water generally, and that's because of how many carbon and hydrogen atoms they have. So they have these big nonpolar parts, which end up outranking the polar parts, and that's why, like for example, in your biodiesel samples in lab, you see that layer separation where the water, the polar stuff, the glycerol and such is on the bottom, and the nonpolar biodiesel is on top, and they don't mix well because of that. Speaking of that, then, if we look at glycerol, this is a molecule that we would expect to be very, very polar, which it is, have very strong attractions, which it does, super high boiling point, and very soluble in water, because now we have 3 OH groups on there. And in fact, pure glycerol is like really thick and kind of syrupy because of those really, really strong interactions creating viscosity and kind of like stickiness. All right, so that's the basics of polarity, intermolecular forces. Work your way through that document and just keep an eye on the goals, that these are the kinds of things you want to be able to do when it comes time for that midterm meeting. All right, well, I will see you in class, and remember that your third module evaluations are due this weekend, so in a few days. All right, see you soon. Bye.